All right, so today we are delighted to have Jeremy Miller here to tell us about stability patterns in the cohomology of SLNZ and its congruent subgroups.
Okay, great. Yeah, so the groups that I'm going to be interested in for this talk are SLNZ and its congruent subgroups. So you pick a number L, you can take a matrix and you can reduce it mod L, and the kernel of that gives you a group homomorphism from SLNZ to SLNZ mod L, and the kernel is defined to be the level L congruent subgroup. So, for example, these are matrices that are congruent mod L to the identity matrix. So for example, this matrix is congruent to the identity matrix mod 3, so it's an element of gamma 2, 3. And yeah, so we're interested in the homology / cohomology of these groups. I'm not a number theorist, so I don't, number theorists care about them because of, automorphic forms and actions of Hecke algebras and, Galois representations. I'm just, for me, they seem like nice groups and I want to learn more about their cohomology because that's what topologists do. Okay. Yeah, so we're going to study the behavior of the cohomology as n gets large and, see what types of patterns there are, and I'll be reviewing, lots of stuff from the 60s and 70s, but also modern stuff involving representation stability, and time permitting, I'll talk about a few new results, although most of the talk will be older stuff. Okay, so here's sort of a picture of what the homology looks like. There's some range in which, so for I sufficiently large compared to n, all the homology is 0. There's a range one if n is very large compared to I, we're in sort of it's a traditional stable range. I'll be telling you about a somewhat conjectural stable range parallel to the vanishing range. And then I don't have any results on this, but how do I get colors? I believe that there should be sort of secondary stability in this region. I'm not going to talk about that, but in this talk. Okay. Oh, do I need to? I'm used to WebEx, and I think I need to clear. Every time I write something, I need to hit clear. Okay. WebEx clears it automatically. Yeah, so there are group homomorphisms from SLNZ to SLN plus 1Z, and similarly for its congruent subgroups, where you just include a matrix into a larger square matrix by adding zeros and ones. And we'll be asking, to what extent does this map induce stability in various senses? So in the sort of the easiest sense, so for SLNZ, it's a theorem of Borel rationally and Routh-Charney integrally that these maps induce in group homology an isomorphism in a range. And these ranges on this page probably aren't sharp and possibly are even misquoted from their paper. There's papers are written in terms of like vast stable range, and different people have different definitions, and I didn't 100% check that I knew which convention they're using. Okay, so for SLNZ, it's just the integral homology stabilizes. For congruent subgroups, you need to invert the level. So if you look at the homology of the level L congruent subgroup with coefficients where the level is invertible, so in particular, you could take Z adjoin 1 over L coefficients, then you also get an isomorphism. So the I homology, if you ignore L torsion, it becomes independent of n for n sufficiently large. And at least rationally, we completely know the answer. So Borel proved that that for any finite index subgroup of SLNZ, there's a map in cohomology from the exterior algebra on certain generators, which is an isomorphism in a range. And one sort of, even if you don't care what the actual answer is, one sort of remarkable corollary is that this answer doesn't depend on which finite index subgroup you're picking. So in a range, the cohomology of SLNZ and in particular congruent subgroups, agree, and it doesn't matter which L you pick. Oh, I guess I forgot to say one other reason to be interested in congruent subgroups is so the congruent subgroup property says that for n at least 3, any finite index subgroup contains a congruent subgroup. So oftentimes you can, if you know something about the homology of SLNZ and you know something about the homology of congruent subgroups, you can sandwich congruent subgroups in between them and prove something about the homology of any finite index subgroup. Yeah, so in a range, the rational homology doesn't see which finite index subgroup you're looking at, which that definitely this is a special property. It's not a property of all finite index subgroups. Like if you think about the braid group and compare it to the pure braid group, the braid group has very little rational homology, but the pure braid group has a lot of rational homology. Okay, so but it's reasonable to say, okay, what happens integrally for congruent subgroups? You said that rationally we get homological stability, but integrally homological stability fails. So the an example of this is a theorem of Lee and Sharba that the first homology of these groups are isomorphic to the first homology group of these congruent subgroups are isomorphic in a range to the this is, I guess, the abelian group of trace 0 matrices with entries in Z mod L. And as n grows, these are trace 0 n by n matrices, so the abelian group grows, so it grows quadratically in n. And yeah, so in particular, we don't have homological stability because there's no way, even if you don't know what the map is, the map can't possibly be surjective because the group is just growing. And then sort of this is, I don't 100% know the history, but whether this sort of happened in parallel with, I believe it happened in parallel with Benson and Tom's work, more thinking about configuration spaces. But so Andy Putman noticed that that these groups exhibit a form of representation stability. So yeah, so one way of saying it is, so although the stabilization map isn't surjective, it is surjective after taking into account group actions. So SLNZ acts on the congruent subgroups via conjugation, and groups act on themselves via conjugation trivially. So this action factors through the quotient, which is SLN Z mod L. And so one, I guess, instance of representation stability is the statement that if you look at the homology for the congruent subgroup of SLN minus 1 and map it to the congruent subgroup for n, that won't be surjective, but it'll be surjective when you induce up. Another way of saying it is the image of the stabilization map. If you look at the closure of that image under the action of SLN, it generates all homology classes. And so I guess originally Andy proved this result with an explicit range, but you needed to invert sufficiently many primes compared to the homological degree. And then Jordan and row-headed primes, but didn't give an explicit range. And then the explicit range was given by Tom and Jordan, and then later improved by rest of the people listed. Okay, so this has some concrete corollaries. Because for FI module people, you're used to seeing symmetric groups, and that's a maybe, I would argue, less natural but more productive way of thinking about congruent subgroups. And sort of a corollary of the proof tells you that these that the homology of congruent subgroups, it grows, but it can grow at most polynomially. So if you pick coefficients in a field, then the Betti numbers agree with a polynomial of some degree, I guess 2i plus 3, once n is bigger than 8i plus 11. Yeah, so so the homology isn't stabilizing, it's not eventually constant, but you have this rigid sort of behavior asymptotically. It can't it's eventually just equal to some polynomial. Any questions? Okay, so now I'm going to sort of shift gears and talk about what happens for large I. So this is the previous story is what happens when n is very large compared to I, and now I'm going to talk about what happens for when I is large. So the theorem of Burrell and Serre that says if you pick any finite index subgroup of SL and Z, then and use coefficients such that all of the torsion in your group is invertible in your coefficients, then the homology vanishes above degree and choose 2. So in particular, if you take R to be Q, then this is just saying then all primes are invertible in Q. So this is just saying that the homology of SL and Z and all of its finite index subgroups rationally vanish above degree and choose 2. On the other hand, if the other extreme, if you take a torsion-free subgroup, then this theorem holds with Z coefficients. So what we're going to do is we're going to declare that the n choose 2 minus I cohomology, or we're going to refer to that as the codimension I cohomology. And the question is, does that stabilize in some sense as n tends to infinity? So if we go back to my picture, what we're saying is look at lines, so above the black line, the homology is 0. And I'm saying just look at the homology or cohomology parallel to the black curve. We're asking, do those groups have stability as n gets large? Oh yeah, so the at least as far as I knew, the first people to propose this idea were Tom, Benson, and Andy, and their and for SL and Z in particular, they conjecture that the codimension I homology is eventually just 0. And you should you might say, okay, why is that a stability conjecture? Well, one way to think about it in terms of stability is if you could show that that a certain stabilization map, I guess this is a typo, this n should be n plus 1, is surjective in the stable range, then it would follow that it's eventually 0, because the curve. Oh,
hey, I feel like I kind of lost the plot for 1 second. I'm just confused about which is growing and which is fixed. I would have thought that n was growing with I fixed, you're at a fixed distance from n choose 2, but it looks like you have.
So there's the one typo. Let me just fix the typo and then re-ask your question. So that n is supposed to be n plus 1.
Right. But I tend to think of these things as like,
I think there's another typo. There should be in greater than or equal to I.
that's my issue.
Oh.
Okay, so
I believe that. Sorry.
okay, if that's what it should be, then I'm happy. That's what I was confused about.
Yeah, sorry, yeah. Hopefully
Okay,
that's what I've been saying. Yeah, you shouldn't necessarily trust what I write or say, but
I think that's what you've been saying up to now. I just wanted to make sure I got it. Okay.
yes, yeah, sorry about that.
We should definitely trust what you're thinking, right? That's the
You
important.
should trust what I'm thinking. Yeah. Yeah, and this, among the conjectures in your paper, this is the conjecture I believe the most. So, okay. Yeah, and so, oh, I forgot to clear it. It doesn't automatically clear it. Okay, so there's a lot of computer evidence for this conjecture, and in codimension 0, it was known since the 70s, and then by work of Lee and Sharba, and a few years ago, Tom and Andy proved it in codimension 1, and then work in progress with Peter and Andy and Jenny. We think that we have a proof in codimension 2. It involves like a 50-page list of like explicit spheres that we filled. And Jenny wrote up the final version of the 50-page list. So I have some confidence that it's right. You know, I have more confidence than if I wrote up the final version of the 50-page list. But yeah, so, you know, if this, you know, there's some chance that it'll turn out that our proof is wrong. Okay. Yeah, so this is, as far as I know, the progress on this vanishing conjecture. So let me sort of change gears to congruent subgroups. So what do we know? Well, definitely the homology doesn't vanish. So in the 70s, Lee and Sharba computed that the top homology of the level 3 congruent subgroup is isomorphic to z to the 3 to the n choose 2. So it grows, you know, like a exponential, I don't know, whatever. It grows very fast. As a representation, this is a representation known as the, you know, this is the Steinberg representation for F3 or for SLN F3. I'll tell you what that is later if you don't know what it is. So, you know, in particular, stability shouldn't be that these groups are just eventually 0 when you look at congruent subgroups. And I'll, you know, remark that we for L equals 2 and 5, we also have a complete answer. So for L equals 2, it's just the Steinberg representation for F2. For level 5, we have a complete answer. There isn't we have like a recursive formula. It's not equal to the Steinberg representation for F5, but from a recursive formula, you know, we can tell you whatever, you know, for any number that that is small enough to write down, we can tell you what the answer is. So for example, when n is 15, so 15 choose 2 is 105. So the 105th homology is this, I think, 73-digit number, is z to this, whatever this number is. So this is joint work with Andy and Peter. And for prime levels, we have reasonable lower bounds. I mean, they're likely not sharp, but they're reasonable lower bounds for the size of the homology and top degree. But it's still, you know, for levels that aren't 2, 3, and 5, complete answer isn't known. Okay. So what at least I think stability should mean for congruent subgroups is just, you know, there should be rep stability. So yeah. Oh, again, some of the typos are still here. This one, did I flip? I think I got N and I correct this time. Is that right? But there's still this N+1 typo. Okay. Yeah.
If you get N and I correct, I will certify that.
Okay. Yeah, trust Andy. So yeah, so Tom, Benson, and Andy say like, okay, you know, there should be some stability pattern, and then Rohit, Peter, and I suggested that it should be this one. It should just be, you know, that these maps should induce isomorphisms in a stable range after, you know, after inducing up. And you know, if you like rep stability, you should think of it as this is like a generation. This is a statement that the codimension I homology of congruent subgroups should be generated in finite degree with respect to the of some category to be presented in finite degree, and all the higher syzygies should vanish, etc. Okay, but you know, one thing to say is definitely these groups grow. You know, this Lee-Sharba example showed they grow faster than polynomially. So definitely we're not, you know, the categories that are going to be acting aren't FI or VIC. They're more complicated gadgets. Okay, so what's known about this conjecture? So the Rohit, Peter, and I proved that the conjecture is true in codimension 0. That sort of followed fairly quickly from known results. The real content of this theorem is we prove that the conjecture is true in codimension 1 for level 3. So the way we're able to prove results about codimension 1 is we used Lee and Sharba's explicit calculation of what the codimension 0 homology is. So that's the only, you know, that's the primary reason why our results are, or one of the main reasons our results are restricted to L equals 3. And you know, this gives you concrete upper bounds on how fast the homology can grow.
Can I ask a question on this slide?
Oh yeah.
So this first conjecture, you're saying that these codimension I cohomology groups should not be a finitely generated like VI or VIC module.
Yeah.
Do you like have an idea of what the structure it should be?
Oh yeah. So I mean, here are maybe two things. Yeah. So well, I mean, one thing is that I guess like in our here are two things that are gonna, or actually I'll just say one thing that's gonna act. So you can ignoring or you can look at the you know, like the GLN version of TCAs. So like monoids in a category, you know, like look at VB with day convolution, like that's a monoidal category. You know, look at the free monoid generated by like a trivial representation in degree 1. That should act on these things.
Oh, is that not VIC?
No, so like in FI it is.
Uh-huh.
In FI somehow imposing commutativity. Yeah, so like the free commutative algebra on a trivial rep in degree 1 forces that it's that the dimensions in each degree are just 1. But here what you're going to get is you're going to get like GLN mod permutation matrices in each degree. So like, you know, bases up to, or like, you know, unordered bases is what you're going to have in each degree. So it's going to grow.
Okay, Rohit made some comment in chat about it being finitely generated over the Steinberg monoid.
Oh yeah, yeah, and yeah, that's also true. And there's some annoying things with units. So the nice thing about the number 3 is the units in Z mod 3 and the units in Z are the same. So some of the things I said might be like slightly false for other, yeah, not necessarily things I've written, but some generalizations of things I've said to level not 3 might be wrong because of units, but it's sort of easy to correct. Like there's this version of VIC with restricted units, and you'd want to do something like that.
Okay, thanks.
So I have just looking at this formula you have. I mean, I'm just trying to guess what the representation theoretic structure is. So it looks like, right, if I were to not have that 3 to the n choose 2 term, that would be roughly like the dimension growth of a VIC module. So should I think of this as like, VIC modules, we require it to have sort of a large invariant subspace for, GL n minus 4, something like that? And am I instead imposing that there's a large Steinberg component?
Well, so, I mean, I started writing something and zoned out. So I was just saying, like, this term you should just think of as the size of Steinberg.
Exactly.
Minus
I mean,
4.
this looks like the dimension of, take like a representation of GL4 times the Steinberg on GL n minus 4 and induce it up.
Yeah, probably. Rohit should say in chat if I said something wrong, but
So I think it's
true.
just it's basically saying that it's generated in degree 4 over the Steinberg monoid. So that's why we get this Steinberg n minus 4.
Oh yeah, and this number is our incredibly crude bound for the size of H, whatever, 4, 2, minus 1, gamma 4, 3. We asked people who like have supercomputers, who I guess where you are, Princeton, to compute this for us. And then like a few months later, they told us that they ran out of space or something, but they're like, built some giant, we're trying to build some giant matrix and then compute its rank or something. And then like whatever matrix, like they couldn't store. So, probably this number is like, 200 or something, but.
But can I ask you, there's a lower bound that's, what is the order of magnitude of the known lower bound? It's pretty big. It's not like, it's not like.
From some paper of Ash, we got a lower bound of like 27 or something. I forget what. Maybe there's a better lower bound. I might also be confusing. Like 27 might not be the right number.
I thought Andy. Okay. Anyway, yeah. I think it's a huge lower bound. But.
There's a huge lower bound in codimension 0. Like Andy has a paper for mapping class groups, and Peter, Andy, and I have, in the paper I talked.
That's what it is. Yeah.
Huge lower bounds in codimension 0. In codimension 1, like we know these groups are not 0 for all n, but yeah, it's possible that we didn't fully understand this paper of Ash, but these stabilization maps for congruent subgroups are injective. So I think this, whatever you get for n equals 3 is a lower bound for all n, or all n bigger than 3. And as far as we know, that's the best lower bound.
Do you expect it to grow like this 3 to the n choose 2 type growth?
Probably. Yeah. I mean, I would. Yeah, probably if our conjecture. I mean, so part of the problem is these, whatever category is acting is very poorly understood. But if you believe our conjecture and all higher syzygies, are being finitely generated, then it probably should say that it has to, like if it's not constant, it's going to have to grow at a pretty good rate.
in codimension 0, it grows in that range. So that's a good indicator, maybe.
Yeah. Anything else before I clear everything? Okay. Yeah, so I guess I've been talking a lot about Steinberg modules, but haven't defined them. So let's define them, and then I'll maybe mention a little bit about the proof. Okay, so for f of field, the tits building of a field is the realization of the proper the post set of proper non-zero subspaces of f to the n. So yeah, like vertices are subspaces, and flags are nested chains of subspaces. And the Solomon-Tits theorem says that this has the homotopy type of a wedge of SNs. So, in particular, all of the, the reduced homology is completely concentrated in degree n minus 2. And so we're just going to define that to be the Steinberg module, and it's GLN acts on the Tits building because it acts on f to the n. So in particular, Steinberg n isn't just an abelian group, but it's a representation. Yeah, and so this vanishing result of Borel and Serre that I quoted earlier follows from this this duality result that says that if you have any finite index subgroup of SLNZ where and you take coefficients where all the torsion primes in your finite index subgroup are invertible, then the codimension I homology of your subgroup is equal to just the ith homology of your subgroup, but now with coefficients in the Steinberg module of Q. And this is true for SLN of other number rings, and then you take Steinberg module of the field of fractions. Yeah, so this immediately gives the vanishing results, because even if you don't know what these coefficients are, maybe it's hard to compute homology with twisted coefficients. It's easy to compute homology with twisted coefficients in negative degree, just 0. So this says that above degree n choose 2, the homology vanishes. And Lee and Sharba's results, you can rephrase them as just saying that the SLNZ coinvariants of the Steinberg module are 0, and the congruent subgroup coinvariants of the Steinberg module, the coinvariants of the Steinberg module for Q, coinvariants with respect to the level 3 congruent subgroup are just Steinberg for F3. Yeah. Okay. So I guess the Tits building is a wedge of spheres. So I'll tell you what these spheres look like, or what. Yeah. So if you take a direct sum decomposition of your field into lines, so your field to the n into n lines, then we'll let S superscript L be the subposet, which are sums of the lines. So, I guess this is a picture in the case n equals 3. So we've decomposed F3 into L or plus L3. And in the Tits building, we get this sphere, this hexagon. So, vertices are subspaces. So L1, L2, L3 are subspaces, but also L1 plus L2, L2 plus L3, L1 plus L3, and edges are flags. So, because L1 is contained in L1 plus L2, we get this edge here. So given one of these direct sum decompositions, you get us into lines, you get a sphere in the Tits building. And, if the lines are ordered, you get a canonical orientation on the sphere, and we'll let A sub L be the fundamental class of this sphere. So this is, and this gives you, viewing the sphere as a subcomplex of the Tits building, this gives you a class in the top homology, which is just a Steinberg module. So you know, what this says is if you have a direct sum decomposition of your field to the n into lines, you get an element of the Steinberg module, and the sphere is called an apartment, and the homology, the fundamental class, is called an apartment class. Okay, and so part of the Solomon-Tits theorem is that the Steinberg module is generated by these apartment classes, and you know, important, interesting question is asking, you know, or I guess you'll say the Ash-Rudolph theorem says that at least when your ring is Euclidean, you can choose these apartments to not only come from a direct sum decomposition, let's say of q to the n, but a direct sum decomposition of z to the n, and that's very useful when studying the action of like SLN-Z instead of SLN-Q. Okay, so what this you know, using these generators, we can make the Steinberg module into a ring. So you know, an element of Steinberg NF is going to be a sum of these apartments, so it comes from a direct sum decomposition, and an element of Steinberg MF comes from a direct sum decomposition of f to the m into lines, and then you can just union these collection of lines, and you get a homology class in Steinberg n plus mf, and you can check that this you know, this is well defined and associative and skew commutative, and so, you know, in particular, if you take the, you know, direct sum of all of these Steinberg modules, then it forms an associative ring. So I take back saying it's commutative. Yeah. Any questions? Oh yeah, and moreover, this multiplication map is equivariant with respect to the natural action of GLN across GLN.
By the way, I think it's worth remarking that you can make this this multiplication map. You can define it on apartments like this, but it can actually be defined at the space level. There's but you have to be a little careful. It's like a suspension involved in there.
You want to suspend twice.
Yeah, you have to suspend twice. So
yeah, or like maybe suspend once and join.
Yeah. There's a suspension and a join. So I wrote this down in a paper with Abner Ash and Stevens.
In like work of Rogness from the early 90s. Yeah, at least the space level construction. Yeah, and that might be that is one efficient way of making it seeing that this is well defined, because, you know, the space level construction is more natural. So there's less things to check. Okay, so this ring isn't commutative, but we want it to be commutative in an equivariant sense. So like in, you know, if you know about TCAs, we want it to be like a general linear group version of TCAs. So you know, we'll let mod GL be the category of representations of the groupoid of just all the general linear groups, or if you like, you can, you know, this is a skeleton of the category VB, which is just category of finite dimensional vector spaces and isomorphisms as morphisms. And this is a monoidal category. So there's a bit with day convolution. So if you have, well, okay, so like what is an object of this category? An object of this category is just a collection of representations of GLN for each n. And if you have two of these, you know, how do you build a new collection of representations? Well, you can just tensor them and induce up. Yeah, and if you were to write this thinking in terms of VB modules, which is categorification, you'd be taking the direct sum of your module, you know, if you're thinking in terms of VB modules, you'd be writing, summing over like ways of writing the field to the n as a direct sum of v and w, and then you'd just be cross out this term and you just be evaluating m on v. Oh, I guess this should be n on w. Yeah, and this is a symmetric monoidal category, and the Steinberg monoid is a skew commutative monoid object in this category. So we think of it as a like as an equivariant version of a commutative ring. Okay. Always forget to clear. Okay, so one of the sort of algebra lemmas that's powering the theorem of about the codimension 1 homology of the level 3 congruent subgroup is this this result that this Steinberg module viewed as an equivariant ring is in fact a Cazul. So that says that the tort groups, you can, if you have a tensor product, you can define tort groups as derived tensor products. The tort groups vanish in all but the top degree. And then I guess the only new result that one of the new results I can tell you about is that joint work with Sander Coopers and Peter and Jenny, we computed the one non-vanishing tort group. So, we computed the Cazul dual of the Steinberg ring to just be, to have in degree n, just the Steinberg module tensor, the Steinberg module. What time am I supposed to stop? Like, this is a 50-minute talk?
Yeah, I mean, if you stop within 10 minutes, that's okay. You can go.
Okay. Yeah, I'll try to. So the last slide is not just says the end. So should be doable. Yeah, so you can compute these Tor groups, just using a bar complex. And so we want these Tor groups to be isomorphic to 0 in a range, and then Steinberg tensor Steinberg in degree n. So, what's a space that's homology is 0 in a big range, and then is Steinberg tensor Steinberg in degree n? We'll just take tits building, join tits building. So the join of two simplicial complexes is a collection of vertices forms a simplex if it's a union of if it's a union of collections of vertices that form a simplex of one with vertices that form a simplex of the other one. So if your simplicial complexes are discrete, so let's say it's 3 points and 3 points, you just put 3 points on one side, 3 points on the other side, and you draw a bunch of lines connecting them. So this is actually just like an honest picture of if you plug in for F2, there are 3 lines. I think there are 3 lines in F2 squared. So and what are all the proper non-empty subspaces in a 2-dimensional vector space? Well, just lines. So this is actually a picture of the tits building, and this whole thing is a picture of the tits building join the tits building for when the field is F2 and n equals 2. And so what we want to do, we want to filter this space such that the associated graded has homology, just the entries in this bar complex. And that will immediately tell you that the Tor groups of the Steinberg module is the same thing as reduced homology of the tits building join the tits building, which will tell you that it's 0 most of the time, and then in top degree it's Steinberg n tensor Steinberg n. So maybe one thing to say is, what does an apartment look like in this situation? Well, an apartment is like a line minus another line. So this is one apartment. This thing is generated by just apartment tensor other apartment. So maybe here's another apartment, and change colors. Oh, there's too many colors, so it's hard to draw this picture. Yeah, so then this gives you a circle So if you take an apartment in the TITS building is just an S0, and then an apartment in TITS building joined TITS building, in this case is an S1, and I don't know, it's the purple. Great. Okay, so what's the filtration? In this case, we're going to filter it. The 0 stage of the filtration is just the orange lines. So what you do is you take the subcomplex where you connect a line on the left with the same line on the right. So this is just, homeomorphic to the TITS building across an interval. So in particular, it has the same homology. This is the 0 stage of the filtration. So it has the same homology as just the TITS building. So its reduced homology is just a Steinberg module. So if you look at the orange, you get a space whose only homology group is the Steinberg F2. And this is the resolution we're going for. And so now what happens when you quotient by the orange? When you quotient by the orange, you collapse the orange to a point. Now there's only one vertex, and then we just get a bunch of loops, and we have a loop for each ordered pair of lines. Well, that's exactly this term, because Steinberg of a line is just Z. So this group is just the free abelian group on the indexing set. Then the indexing set are just ordered pairs of lines that add up to F2. Yeah, so this in particular gives a new proof of causalness and identifies the top homology with Steinberg tensor Steinberg. I guess I'm didn't plan on it and don't have time to exactly say how this is relevant to congruent subgroups, but causalness of Steinberg was used to study the codimensional homology. Okay, that's all I have to say. I sent this picture to Jenny, and she decided to go with a different picture for the website, so added it here.
Great, let's thank Jeremy. Are there any questions for the speaker?
Yeah, I've got a question. The Steinberg algebra type thing that you were writing down before. So it's causal. Do you know anything else? Do you expect like a Noetherian result, for instance?
I don't know anything else.
Okay.
Yeah, I don't know if Rohit wants to say something or either.
I think I was thinking about noetherity even like when so I was thinking about noetherity even in characteristic 0, but I couldn't figure it out. So we don't know yet.
Okay.
I was just doing some calculations for this representations over this Steinberg algebra thing. Do you, at least in some of these low-level calculations I was getting, do you expect there to be some sort of kind of multiplicity type stability like we see for, say, VIC or VI modules?
I don't know what the irreducible representations of SN are rationally, so I'm the last person to have an opinion on this.
So Rohit, maybe do you have an opinion on that?
I guess you can think of these as partition valued functions, and
right.
Like
so in particular, if you look at it as partition valued functions, I think that for these, the stabilization map should be to add a box to the first column of the first partition.
It could be. I'm not entirely sure.
Seems to be what's happening in like small examples I worked out.
I think if someone can correct me if I'm wrong, because I don't know this stuff very well. But like there's this class of unipotent representations if you're working with GLN over a finite field at least, right?
Mm-hmm.
Right. Mm-hmm.
And then this Steinberg thing is probably pretty close to like the signed version of FI if you just restrict yourself to that class, right?
One problem is that we are talking about the induction product is
right. If you use the different tensor product, that's true.
Yeah. Mm-hmm.
Okay.
Are there any more questions for Jeremy? Okay, so I'm going to now stop the recording. So goodbye, everyone listening to the recording.